In this lesson, we're going to continue our study of Taylor and Maclaurin series and polynomials. We've learned what each one is, that a Taylor polynomial is a polynomial representative of a function, and a Maclaurin is just a specific type where our center is at x equals 0. Okay, we've done a couple examples of finding Maclaurin polynomials for a couple given functions, specifically a sine function. So let's look at a couple of others. In example 5, it says find the Maclaurin polynomial of degree n equals 7 for f of x equals cosine of x. Use it to find the first 4 non-zero terms and the nth term for the Maclaurin series for f of x equals cosine of x. So again, because this is named Maclaurin, we know that our center is at 0. Okay, we know we want a degree of 7, so we're looking for our P7. And going back to our formula, we need our initial function evaluated at the center, and then we also need the first, second, third, and so on onto the 7th derivative of our function evaluated at that center, which for our case is 0. So let's start by finding that. That's a list. I like to just kind of make a list off to this side. Starting with, let's see, we said this was cosine. Is that right? Cosine of x. Okay, derivative of cosine is opposite of sine. Derivative of opposite of sine is opposite of cosine, and so on. Okay, sines and cosines have that cyclical derivative. All right, and then we want to evaluate it for our center, our x equals 0 or c equals 0. All right, so for x equals 0, cosine of 0 is 1. The sine of 0 is 0. The opposite of 1, 0, 1, 0, opposite of 1, 0. All right, so we get that cycle that we recognize is real similar to our when we started off with sine of x. So those are going to be our coefficients that we're going to put into our series here. So let's get started. So we're looking at starting with n values of 0 and going on 1, 2, and so on. All right, so our first term is just f of c. So that's just a 1. All right, we're going to add to that the second derivative, which is 0 over 1 factorial times x to the first power. And then we're going to add to that our next derivative, which is the second derivative, which is negative 1 over 2 factorial times x to the second power. So again, remember, these n values are plugged in here and here, and essentially in the nth derivative at our center of this numerator here. All right, so let's keep going. So plus 0 over x cubed plus 1 over 4 factorial times x to the 4th. And we're going out to n equals 7, so we've still got a couple more terms to go. Make sure you give yourself space. Oops, forgot my x. All right, let me make sure I'm doing the right thing here. Over 6 factorial Okay, so when we get to our 7th degree monomial, then we can stop. That is our p sub 7. But let's simplify. Maybe let's take this designation down here. We really want to save that for when we simplify it. All right, and this is, we're approximating cosine of x. So let's put that. So cosine of x is approximately our p of x. Let me see if I can write that p a little bit better. All right, and let's see what happens when we simplify. So we still have 1. This is a 0, goes away. We have minus 1 over 2 factorial. We don't need that 1 there. We can put that x squared on top. Next term goes away. Then we've got addition of x to the 4th over 4 factorial. Next term goes away. Lost everything. Come back to me. Here we are. What do we got? Minus x to the 6th over 6 factorial. And then that last term is gone as well. So even though this is a degree n equals 7, we actually don't have that term because it has a 0 in front of it, but we leave it just like that. All right, so P6 and P7 would be the same for this function here. All right, so boom, there's our Maclaurin polynomial series to approximate cosine of x. All right, they also ask for, what do they say? Use it to find the first 4 non-zero terms. We got that. And the nth term. All right, so the nth term, if we come over here to the side, let's give ourselves some space. And we just kind of start with those first 4 terms. And then if this were to keep on going, okay, and we came up with kind of our general rule for that, then we would get, let's see, we've got an alternator, so -1 to the n power. We've got, in the numerator, we've got an x to the, let's see, those are even numbers, so to the 2n, all over that same value, even numbers, but factorial. Okay, so that would give us our nth rule. And then if it kept on going on to infinity, then we could write it as an infinite series using just that rule. All right, and again, the powerful thing about this is a polynomial series that is approximating a cosine function. All right, that's pretty bonkers. If we look at the graph, kind of like we did with sine, let's see what it looks like. Again, just to illustrate, I think it's really powerful to look at the graph and see what is actually happening as we model this function with a polynomial series and as we put more and more and more terms to it. So there's our cosine function in blue. I've already put our function in here. All right, so as a series going from 0 to whatever a is, I've made a slider so I can kind of increase that one by one. So this is giving us those partial sums of that rule for our polynomial function that we just put in. So right now, it's not a good approximation. Only right at 0, where our y value is 1, is it good. Remember, that first degree of a Taylor or Maclaurin series is always going to be a tangent line to that point. Okay, so when we start to add on terms, so here's when a equals 1. Now we can see a way better approximation around that center. And then we start to add on more and more terms, and we start to see, I'm going to set this in motion, and watch what happens, how it kind of maps to this cosine function. All right, so again, it's just adding on more and more of those terms. What? Is that crazy or what? All right, we can zoom out and see that it's still going. All right, and you can see the more and more terms. So it's adding up. Let's see if I can pause it here. It's adding up those first 25 terms of that series. And look at how it modeled that cosine function. And that radius of convergence gets wider and wider the more and more terms that you put in there. All right, pretty rad, pretty rad. All right, so let's move on. Example 6 says, find the Maclaurin polynomial of degree n equals 4 for our function e to the x. Ooh, okay, so switching up functions again. So far we've just been doing trig functions. Now we're switching to exponential. Use it to find the first 4 non-zero terms and the nth term for the Maclaurin series for f of x equals e to the x. Okay, so same deal. This is a Maclaurin polynomial, so we know our center is 0. All right, that's all we've done so far. In our next example, we're gonna switch it up and move away from that center. They want a degree of 4, so we need to find our function evaluated initially at 0, and then our first 4 derivatives. All right, so let's do that. Our function is e to the x. What's the derivative of e to the x? It's just e to the x. Derivative of e to the x. All right, again, over and over. Again, this is that unique function where its derivative, its slope at any point is the same as that y value. Okay, so this will make things nice. We are evaluating this for, again, our center is at 0. So for x equals 0, anything to the 0 power, boom, is 1, is 1, is 1, is 1, is 1. So each of those coefficients are going to be 1 with that factorial and with that x in there. All right, so let's do that. Let's see what we get. Okay, so for that first term, we're going to get just our function evaluated at 0, which is just 1. Oh, that's big. All right, plus our next term 1 over technically 1 factorial times x to the first power, plus 1 again over 2 factorial times x to the second power. All right, do we see the pattern here? This one kind of simplifies a lot nicer. Okay, plus 1 over 3 factorial times x cubed, plus 1 over 4 factorial times x to the 4th power there. Okay, so let's see. The only thing we can do to simplify that, all right, so e to the x is approximately this 4th degree polynomial, which is 1 plus, we don't need that 1 factorial, 1 plus x, plus we can say x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial. So there's our piece of 4, our 4th degree Maclaurin series that, again, I encourage you to try to explore this one. Graph e to the x, graph this series and see how it kind of maps to, gets kind of stitched onto that e to the x, and more terms that you put in there. It's pretty cool. They also ask for the nth term. Okay, so let's do that as well. Let me grab that one. All right, so we've got, I'm just going to kind of copy this down here. Why don't we change colors? Are you not gonna let me do that? All right, well, I'll do it myself. All right, so 1, what do we got? Plus x. All right, and so on and so forth. We want to get to the nth polynomial. Maybe we didn't need that many terms. But that's okay. So dot, dot, dot. So we've got no alternating here, so we don't need that -1 to the n power. But we've got our variable in the numerator being raised to the nth power. All right, so again, n equals 0, 1, 2, 3, 4. And we're just saying n factorial in our denominator. So there's our nth term for our Maclaurin series for e to the x right there. All right, example number 7. Find the Taylor polynomial of degree n equals 4. For f of x equals natural log of x centered at c equals 1. Then use p sub 4 of x to approximate the value of the natural log of 1.1. Okay, so switch into Taylor polynomial. Notice they give us a center. If it's other than 0, then they give us a center of 1. So what are we doing here? Let's start off with our same beginning that we have been doing in the past couple of problems for these Maclaurin series problems. Let's find the, evaluate our function, all right, which is natural log of x, and find its derivatives. In this case, we need to go down to the fourth derivative and then evaluate it at the center. All right, so derivative of natural log of x is 1 over x. I'm not giving myself enough space here. Derivative of 1 over x is opposite of 1 over x squared. 2 over x cubed, and opposite of 6, 3 times 2 over x to the 4th power. Okay. Let's evaluate that at our center. All right, so our center is no longer 0. Our center is at 1. So let's plug in 1. Okay, natural log of 1. Natural log of 1. E to what power gives you 1? That's 0. 1 over 1 gives us 1. 1 squared is 1. Negative 1 over 1 is negative 1. 2 over 1 is just 2. Negative 6 over 1 is just negative 6. Okay, so we got a little bit more flavor going on in our coefficients here. So now when we plug those in, we'll have to make sure we be careful and plug those in accurately. All right, so let's start off. Let's revisit our notes here to make sure that we plug in the right formula since we're switching to our Taylor series. So the only difference here is that we are we've plugged in our center. That's something other than 0, and instead of just plain old x, we're looking at the difference of x and the center. All right, everything else is the same. Everything else is the same. So this is not a big stretch from a Maclaurin polynomial. We just got to make sure that we key in those slight differences. Okay, so evaluate our first term. Natural log of our center 1 is 0. Okay, our next term, we've got a coefficient of 1 over 1 factorial. And again, we want to do, let's see if I can keep both of those in. We want to do not just our x, but our x minus our center. All right, that's raised to that first power. Plus our next coefficient, which is negative 1. All right, so we're going to have an alternating series here. Again, still over 2 factorial, still times x minus 1. Now we're raising it to that nth power. Again, our n equals 0, 1, 2, 3, and we'll get to 4. What's next? So plus our next coefficient is a 2. So 2 over n factorial times x minus c to the nth power plus our fourth derivative at c, which is negative 6 over n factorial times x minus 1 to the nth power. Okay, so that is our, once we simplify, that is our p sub 4. So let's do that. Ooh, you're going to let me switch now. Thank you. All right, and this is approximating the natural log of x. So we can say ln of x is approximately this p sub 4. So this 0 goes away. No other 0 terms in here. So we're just going to simplify any 1s and any coefficients. 1 over that is just 1. So we start off with the x minus 1. I'm going to keep those parentheses there since we're going to have them for the rest of our terms. Minus, I'm going to go ahead and put that variable in the top of that fraction just like we typically did there. And we'll see as we get out here that we can actually simplify these quite nicely without the factorials there. So 2 factorial is just 2 times 1 plus, and we've got a 2 here, but 3 factorial, remember, is just 3 times 2. So we can just leave that 3 in the denominator. We have x minus 1 to the third power, or you can leave it all there. It's no big deal if you leave the 2 and the 3 factorial there. Not a big deal. It's just going to be a lot easier to write our nth term, which we're not even asked to do on this one. But if we were to write our nth term, come up with a rule for this if we do a little bit of simplifying first. All right, that's the advantage of doing that there. All right, so minus, and again, 4 factorial is 4 times 3 times 2. Well, 3 times 2 is just 6. So that goes away. So we're left with that 4 there. Still have the subtraction, and we still, which we got out here, and we still have the x minus 1 to the 4th power. Okay, so simplified. That is what our p sub 4 looks like for natural log of x. So do we answer all the questions? No. We were asked to approximate the value of the natural log of 1.1. Okay, so a little bit off of that center. Use it to evaluate. So let's do that. So the natural log, let's try that again. Natural log of 1.1 is going to be approximately p sub 4 of 1.1. And now we're just going to plug that into our x in each of these terms as we go across. I'm going to need to make that smaller. All right, so 1.1 minus 1 is just 0.1. Again, 1.1 minus 1. Every time this is just going to be 0.1. Should I write it like that? Yeah. 0.1 squared over 2. Plus 0.1 cubed over 3 minus 0.1 to the 4th over 4. All right, and if we were to put that in our calculators and see what we get, we should get something like 0.0953. All right, and again, that's our approximation for the natural log of 1.1 without even using a log. We didn't do any log calculations there, other than initially when we found that coefficient, doing that log of 1. But once we got our polynomial, used only these monomials, these individual monomials, plugged in our value to approximate natural log. It's pretty rad. Okay, we answered all those questions. Example 8 says, suppose that g is a function which has continuous derivatives and that g of 2 equals 3, g prime of 2 equals negative 4, second derivative of g of 2 equals 7, and the third derivative of g of 2 equals a negative 5. All right, write a Taylor polynomial of degree 3 for g centered at 2. Ooh, so this one's a little different. They don't give us our initial function as a rule. They don't. They do give us the center here. All right, centered at 2. And they want a Taylor polynomial of degree 3. So they want, again, Taylor centered at 2, degree 3. So they want a piece of 3. So let's find that for them. All right, so how are we going to do that without a function? Well, they give us all of our coefficients, essentially. We're going to follow that same rule of just borrowing this last example as our reference. We're going to take that n value factorial in the denominator, times x minus our center, which in this case is going to be 2, raised to that nth power. They give us all of these values. All right, so these values here are the same as those values that we would have gotten if we had a function and we made our little list out to the left here. All right, that's those same values. They actually kind of did a little bit of the work for us. We just have to identify that that's what they've done and be able to put those in the right spots to form our polynomial. Okay, so kind of recognizing what they've done for us and then putting them in the right spot. So we always start off with our original function evaluated at our center. That's our 3 here. So our first term is going to be 3. All right, our next term is a negative 4. So we're going to take away that 4 over 1 factorial times x minus our center, 2 in this case, raised to the nth power. That's just 1 so far. Again, n equals, let's see if it'll let me switch. Yeah. All right, so we're starting off at 0 always, 1, we're going to get 2, and then it says degree of 3. All right, if it helps, write out those n values underneath so you know what to plug in where. All right, all it takes is to miss one sign, or to miss an exponent, or to raise it to the wrong power to mess up your whole function. All right, so plus, and now we know that it's going to be 2 factorial times x minus 2 to the n power, to that second power. But what's our coefficient there? Well, we've used g to the first derivative. Now we need second derivative of 2, which is 7. So that 7 gets put there as our coefficient of the rest of that. And then moving on to our next term, we keep up with the alternating. So we have a minus 5 over, again, n factorial to the x minus our center to the n power. Okay, so there's our polynomial function. I think we can clean it up a little bit. Not much. We can clean it up a little bit. All right, 3 can't be changed. This is just minus 4 times x minus 2. Could we distribute that through? Yes, but don't. We want to kind of keep the pattern going. And I think if we get rid of these factorials and kind of treat these as those coefficients, we'll be doing just fine. Over 7 over 2 plus 7 over 2 times x minus 2 squared minus 5. 3 factorial is 3 times 2 is 6. Times x minus 2 cubed. All right, there's our Taylor polynomial of degree 3 for function g centered at 2. Again, we don't know what g is equation-wise, but we know that's the third degree polynomial. Given what we were given, that's all we need. Oh, example 9, last one. This one's got 1, 2, 3, 4 parts. Let's look at this. All right, one at a time. The setup says let p of x equal be the fourth degree Taylor polynomial for the function f about x equals 4. Assume f has derivatives of all orders for all real numbers. All right, so similar to the last one, they don't give us the original function f. All right, they do tell us what P of X is. Okay, so that's different. Notice they don't have any factorials in there, so we're going to have to maybe reverse engineer that some come one of these problems down here. And it says 4th degree Taylor polynomial, and here's our center C. All right, assume it has derivatives for all the numbers. All right, so find f of 4. Where do we find that? Well, 4 is our center. All right, thankfully that's the number that's in there. Otherwise, we wouldn't, we couldn't evaluate that for any other number. F of 4, that's going to be our initial term there. All right, 7. So f of 4 is 7. Again, going back to our notes, make sure you are revisiting your notes and you're using these to help you as you practice these problems on your own in just a little bit. There's our first term. All right, f of c for both our Taylor and polynomial, doesn't matter. Shouldn't be a variable in that first term. All right, unless it turns out to be 0 and we simplify it later on. Okay, and then we want to find the third derivative at 4. Okay, so if this is f of c, this is f, well, contained in it is f prime, f double prime, and f triple prime. But remember, this term here, all of this, -2, is not just the third derivative of 4. It's the third derivative of 4 over, what do we have? 3 factorial. Okay, so be careful. We can't just steal that -2 as our answer. We've got to put it in context of that whole coefficient there. But we can solve for this now. So 3 factorial is just 3 times 2. Okay, so multiply both sides by that. That's 6. 6 times -2 is -12. And boom, we got our third derivative by itself. -12 is our third derivative of f at 4. All right, awesome. Part B. Write the second degree Taylor polynomial for f prime about x equals 4 and use it to approximate f prime of 4.3. Whoa, okay, so second degree Taylor polynomial for f prime. All right, wait a minute. So we don't have f prime. We've got f prime at 4, which we could get from this term right here. But we don't have the Taylor polynomial for that. So what can we do? F prime. Let's see if I can zoom in here. All right, our function is going to be approximately our Taylor polynomial if we took the derivative of it, all right? Because they give us that. They give us, where do we go? They give us P of X. So if we just take the derivative of that up until the degree that we need, that'll give us approximation for our f prime of x. All right, so let's see if I can get both of those in screen here. All right, so we're going to go term by term. All right, so this first term here, let me switch up colors. Derivative of 7 is 0. Boom. Subtraction. Derivative of 3 times x minus 4. Well, derivative of x is just 1. So we're just going to get that minus 3 there. Plus, now we've got x with a power. So 2 times 5. And then raise this to the 1 less power. And then chain rule, derivative of x minus 4 is just 1. So times 1. And then minus 3 times -2 is 6 times what's still on the inside, raised to 1 less power. Chain rule times the derivative of the inside is just 1. We don't need that there. And then boom, we're asked for the second degree Taylor polynomial. We just got a second degree term, so we can stop right there. All right, we don't even need to take the derivative of that last term there. So there, maybe let's simplify and let's get this 0 out of there. So our f prime is approximately, and we're doing this, what are we doing this for? We're using it to approximate f prime of 4.3. So f prime of 4.3 is approximately p prime of 4.3. All right, we don't need that 0 there. It's going to be minus 3 plus 10 times, and then 4.3 minus 4. We're plugging in 4.3 into our x. It's just going to be 0.3 minus 6 times, again, another 0.3. If we go ahead and simplify that, squared. All right, let's see. We can do this by hand, I believe. 10 times 3/10 is just 3. 3 plus 3, it's a 0 pair, so we're just left with this piece here. 3/10 times 3/10 is 9/10. So 9/10 times a negative 6. What do we got there? 2 goes into that. 5 times, 2 goes into that 3 times. So we get negative 27 fifths, or negative 0.54. Okay, so there is our approximation for f prime of 4.3 right there. All right, using our second degree Taylor polynomial for that derivative there. All right, pretty nice. So we can take the derivative of that Taylor series to approximate the derivative of the original function. Okay, part C. Write the fourth degree Taylor polynomial for g of x equals the integral from 4 to x of f of t dt about the center x equals 4. All right, so we're going to do something similar to what we did with the last problem. And we're going to say, hey, integral. We don't know the original function f itself. We just know a Taylor polynomial for it. So g of x, we're told, is the integral from 4 to x. And of f of t dt. All right, what we can do is we can say, okay, so similar to the last one, where to find the derivative, we took the derivative of each of those terms in our p of x. Let's do the opposite. Let's take the antiderivative. So we're going to take the antiderivative, all right, from 4 to x of that first term up there. See if we can get that in screen. Can we do that without making it too small? I bet we can. Or not. Yeah. Okay. Again, I'm looking up at this first term here, going back to our original p of x, that integral of 7 with respect to x. All right, plus the integral from 4 to x of that next term, which is negative 3 times x minus 4 with respect to x, and so on. We're going to take each of those terms, take the integral one at a time. Right, and we want to go, what does it say? Fourth degree. Thinking ahead, looking at our integral. If we integrate this one, we're going to go up one. We're going to get our fourth degree here. Let's stop. We don't need to go any further. All right, if you did write down the rest of those terms and integrate them, then that's fine. No big deal. You'll just chop it off when you get to the simplifying stage. All right, which is what we're doing now. So we have just integrated whoa, that's not an integral sign. Where'd that come from? From x to 4. Our polynomial series, our Taylor series. So let's do that. So this is going to be 7. All right, so thinking about this is essentially a definite integral. So integrate this, we're just going to get, pull out that 7. This becomes x. So this is going to be 7x minus 7 times 4. Okay, or we can pull out that 7 and get 7 times x minus 4. Does that look similar? Does that look familiar? Plus, and then let's kind of do that for the rest of them. So pulling out that negative 3. If we integrate this, we're raising that to the second power. And we're dividing by that. All right, when we do our minus 4 in this case, 4 minus 4 is going to give us 0 here. So that's all going to go away. So just like when we did definite integrals up to x for other functions in the past, we're going to get that essentially that indefinite integral. So plus, pull out that 5 over, raise that by 1, 3, x minus 4 to the third power, minus 2, raise that by 1 is 4. It's 2 fourths. Let's go ahead and simplify that to 1/2. And x minus 4 to the 1 bigger is 4. Boom. And we don't need it. Since each of these were technically definite integrals, we don't need a plus c. This is representing the integral from 4 to x of our original function f of t dt. Again, that would be the that change over time, total change over time from 4 on to whenever that x value is. All right, pretty cool. We can do that with the Taylor polynomial again. All right, geek out with me for a minute. Let yourself go. You know you want to. Come on. Part D, last one. Can f of 3 be determined from the information given? Justify your answer. Nope, it cannot. We only have information about f of 4, about centered at 4. All right, since p of x is centered at f of x equals 4, we know our function evaluated at 4, the derivative evaluated at 4, the second derivative, and so on, evaluated at 4, but we don't know what it is evaluated at x. So f of 3 cannot be determined. Okay, so those are a couple of examples of problems having to do with Maclaurin and Taylor series. I encourage you to try these, practice these, and check your work with graphs, check your works with the keys on the unit plan, and come with questions next time we meet.